Thank you, Simon, for the introduction. Hi, good evening. My name is John Min, as Simon mentioned. I didn't put a slide together to introduce myself, but basically Simon did a good job. Well, educationally, I am a biomedical engineer. Specific emphasis on nonlinear system simulations. Basically what that meant was I did a lot of programming to model hardware. My graduate work was in emulating a drunk's walking pattern. Somebody who's drunk, how they walk, where they have limited control. So it was partly control systems and partly its non-predictability. So that's how I got into processors. Like any Asian mothers, she wanted me to be a doctor. So I tried medical school for her, didn't like it, and I became an engineer and was okay. So let's talk about the one thing that's big interest right now is AI. What's artificial intelligence? There's something in here that I was really surprised when I started looking at this probably about 6 months ago, a year ago, from a processor point. Just the scope of what it takes to do AI. All of us probably have phones. I use Apple. And if you follow, so I use Apple, so I don't know much Android, but if you follow this, iPhone 4S came out 6-7 years ago. When they came out, Siri spoke a lot about she didn't understand. Today, Siri, I haven't had Siri tell me she didn't understand something I asked in months. So it's gotten better. Let's see what it took to get it better. But quick words from my sponsor. If you don't know, MIPS used to be an independent company. We're about 35 years old. We went into many different iterations. We started with a computer servers architecture. SGI, Silicon Graphics Inc. was one of the bigger server companies. And then we became a computer company, MIPS computer company. And then Microsoft killed it by pulling the Windows NT. So MIPS actually ran Windows NT 64 bits before Intel. So that's the history. Today, we're a 32 and 64 CPU architecture and IP core licensees. Okay, we don't make anything ourselves. We're idea guy. We design the CPU, we license for a lot of people to make. Okay. We're right down the street in Santa Clara. We're about 200 people, and we got spun out from Imagination about 2 months ago. So, the heritage-wise, first MIPS architecture was defined at Stanford in the early 80s. And then we grew out 1986 with the CPU product, R2000 shipped, R3000, R4000 became independent in 98. And then we started getting into a lot of different applications. Number one application even for us today is networking. Okay, we do networking well. Networking has evolved into the last thing we're doing is we're in a lot of the LTE base stations, LTE modems. Data processing, that's what MIPS does well. Kind of things we do, set-top box, DTV, 5G, 4G, telephones and base stations, IoT, autonomous applications, and then how to use IoT. Biggest consumer of AI today is two things. Speech recognition, and hottest place is the autonomous driving. So, it's really hot. Every field, computer vision, different things, sales. When you walk, pretty soon when you walk through a mall, the kiosk will know you from the phone and give you advertising to what you're at, right? It already happens in browsers. Did you notice that? I've got to search something on Google, went to a website, and I get popped in something similar. Voice interface, robotics, automotive, healthcare. Healthcare is big, security. So there's 60 plus companies announced that they're doing AI. What that means is there's probably 10 times more companies, stealth startups, trying to do AI. But what's artificial intelligence, okay? I used to know this as control system, right? What you want to do is design a circuit to automate to do something. Okay. Thermostat, I grew up with that thermostat. You set a temperature at your house, and they kept my house temperature at a certain temperature. It became digital thermostat, got a little more accurate. It's getting more accurate, which is nice, but sometimes you don't want that accuracy, right? You want a little variation too. So we're increasing smartness and precision. Another good example in automotive, the automatic cruise control systems. Used to be you set a speed and you had to monitor it. Now cars do that for you. Okay? Car will decide if you're too close or not. If you're too close, it'll slow down. If you're far enough, it'll accelerate to speed you set. So this is the simplest form of AI they would probably use every day. So, what's hard about AI? Okay, we're people, we could work with this. And I found this picture a couple days ago, and this was the right thing. From the top, something's falling on your head. What can you say? One, watch out. Two, you could say what it is. You have a 1,000-pound block falling on your head. Okay? Both answers correct. Which one's the right one to say? Okay? So you could be precise. You could be significant. I used to work for someone, a CTO of company, and I don't like specifics because things could change. So I said something like 28.7% probability something would happen. Well, actually, it was 28.7% probability. What I said was about 30% probability. Because it was really 28.7 plus or minus 5%. And the CTO jumped up and said, John, stop exaggerating. It's only 28.7%. Right? Okay, was it important to correct that? Is that 1.3% important? It really wasn't. But he just liked arguing. So, what's really hard is not the AI, or not the answer, but getting the right answer. Okay. So, what does it take? What does it take to get the right answer? Andrew Ng mentioned in a conference for Baidu speech recognition training, teach the AI brain to do the right voice recognition. It took 10 exaflops of cycles or floating point calculations. I had to look up what exa was. Okay. It's a really big number. And they used 4 terabytes of training data. So they recorded this voice, recorded responses, 4 terabytes worth of data. So we'll talk about how long that might have taken. Chris Nickel in Embedded Vision Summit mentioned about their wave computing processor. Okay. Wave computing processor is very big, lots of execution engines. What capability do they have? Well, they have about 250,000 processing elements. Okay? And running at their mega speeds, or giga speeds, they estimate they could do about 3 peta operations per second. Okay? But I think they're running like 10 gigahertz, right? They're very high. So, with a lot of data bandwidth, 4.5 terabytes a second data bandwidth, it's just amazing amount of resource. So, one thing we need to know if we want to do AI, know what these units are. Okay? Exa, zeta, and iota. I've never actually heard that. So, the black box, how do we make it happen? Well, you need to train, just like what people do, or machines do, we need to get a lot of experience with the situations are. So the training data, I go to a restaurant, I eat, and I evaluate what kind of service I got. Did I get the water on time? Did I have to wait a long time? And eventually that determines what my response is, or tip them out. For the machine, how does machine evaluate? Is waiting 5 minutes enough? 10 minutes? 30 minutes? How do you know it's right? And different restaurants, like McDonald's, waiting 5 minutes is a long time. But a very fancy French restaurant, maybe 30 minutes, 1 hour is okay. So there's a lot of situations. And how do we do it? So where did we start? Okay. 1935, Turing machine was designed to break German encryption codes. Okay. That's one of the first modern computers that most people say was a processor modern computer. Enigma, yeah. So the other thing that's common, everybody knows, movies or space buffs, Apollo guidance computer ran at 2 megahertz in 1966. That's a really fast. I know that because first computer I bought in 1984 only ran at 4.77 megahertz. Okay, and it took me 5 years to pay it off. IBM PC, by the way. So the magic black box, that black spot, what do we put in? Okay, so I'm going to concentrate on the hardware, what that black box is, because we know what the input is. For speech recognition, it's 4 terabytes of training data. Okay, so how do we process this? There are a lot of ways to do it. There's CPU, okay, it's general purpose, and DSP, floating point SIMD units, GPU, a data flow processor. It's relatively new. Before a year ago, so just to let you know, I retired about 2 years ago for about a year. I did something different. I came back part-time because my wife kept asking me to do more things. But data flow processor, if you asked me 2 years ago what it was, it's a data engine, data pump that move data. Data flow processor today is being referred to as something that could not only move data, but process a lot of data. So things are changing. And then lastly, dedicated accelerators. Okay? If you know what you're doing, design a dedicated engine, and you could do it. Most common accelerator that we see today is butterfly multiply operation. Okay, do you know what that's used for? FFTs. I could accelerate FFT calculation 8 to 10 times in software if I had that one specific instruction. Amazingly, not many processors have it because not many processors are designed to do a lot of those calculations. So let's look at CPU. CPU is jack of all trades. Okay? That's like me. I'm a biomedical engineer. I know biology, I know medicine, I know electrical engineering. So I could do a lot of things, but what it's good at, what it's really good at is decision making. Processor could take input, decide what to do. Given, or choose options, it could do very well. It's master of none. It's not excellent at, well, decision making it does well, calculations, data movement. But generally, performance is generally bound by memory movement, memory bandwidth. Why? Because it generally has the caches, instruction and data caches. Caches, by its nature, is not predictable or deterministic, unless you program it that way. And that's not many people can do. And what can you do? 1 or 2 math operations per clock cycle. It's running gigahertz. You could do gigamax or gigamultiplies, gigafloating point operations. Not very exciting, but most of the time it's okay. Now I need to do more math. Remember? I did, what was that Baidu? 20, let's go back. By the way, I'm not very good at memorizing specific numbers. About 10 exabytes, exaflops. 10 times 10 to the 18 operations, floating point operations. So, if I do 1 per cycle, then I need 10 to the 18 seconds. Okay? That might be a long time. So, what do CPU generally do? CPU issues, you throw lots of processors at the problem. As long as you could divide the problem, then I could scale this until I run out of power, silicon, or frequency, or money. So, one of our processors, i6500, I could put up to over 1500. It's designed that way. In practice, anybody putting more than 512, maybe even 256, needs some specialized, it's better to go specialized engines rather than doing a CPU. So, this will surprise a lot of you. This slide is one of my key things I lecture on. Let's say you have a 1 gigahertz processor. How much time does it spend working if you do calculations? Okay. In reality, you're going to execute 10 to 20 instructions before you miss in the cache. Okay, remember the cache wasn't deterministic. So about 10 to 20. And then main memory out here might be 50 to 100 cycles. So let's say it's 100 cycles. I did about 15 operations. I waited 100 cycles. So I did 15 units of work, took 115 cycles. I only worked 13% of the time. CPU was idle 87% of the time. Okay? Any processor, well, some processors are better or not, but most efficiency, you're going to sit around 10 to 20% for a general purpose processor. That's why a lot of processors says level 1 cache, that's the level 1 cache. You have level 2 cache, level 1 cache is 1 cycle. Level 2 cache, hopefully it's about 20 cycles. So now, you bring this down to 20, you could get close to 40% efficiency with big memories. That's why the Intel processors put level 3 caches, sitting about 40 cycles. But these starts getting longer. So idea is, think about this one. You got to get the data closer to the processor. And all of the architecture I'll talk about, they do that. So let me skip that, I'll come back. So, digital signal processor, what is it? It's a CPU that's been so optimized for math operations, okay, it's lost a C. It doesn't do decisions well. It's designed to be linear. It does linear calculations. Okay. So it does linear calculations from dedicated memory. That's it. That's how DSPs perform the calculations very well. They have dedicated memories, and then they have dedicated memory controllers. They'll feed that memories constantly. So, a couple of things from this block diagram. Program memory space is limited, so it's actually doing few things. Okay? But the data set could be much different. Image processing. I'm looking for specific pixels, specific voice patterns, so I know how much the program is. Pictures might change, voice patterns might change. So, a lot of these CPUs have gotten some capabilities, so most DSPs have actually gone down in usage. There's actually used to be about 10 DSP companies about 15 years ago. Now, there's probably one company that's really existing. What can you do? The bigger DSPs could do about 1,000 operations per clock cycle. Okay? They run 1, 2, 3 gigahertz. DSPs tend to run a little bit slower. Reason for that is these program memories and data memories, they're big memories, so it takes a long time to propagate cycle. So, a couple other units. Now these goes generally to the processor. Floating point unit and SIMD. Okay? Floating point's easy. Floating point actually is better processing because the world is floating point. It's analog. But it's expensive to calculate as well. So floating point units generally 64 bits, maybe 128. So you could do 2, 3, 4 operations per clock cycle. But it runs with CPU, so you could divide the tasks as well. Now, the SIMD is more interesting. Okay? Intel calls theirs SSE or MMX. ARM calls theirs a neon engine. So basically what that is it's a single instruction, multiply, mac, divide, whatever, and single instruction, multiple data. So I'm doing multiple operations at the same time. Most common at 2056-bit SIMD. What can you do? You could do one or two 56-128-bit operations. You could do two 64-bit operations, 432-bit, up to 16 8-bits. Depends. If it's wider, you could do more. And this is what the picture looks like. If you do one at a time, this is what you do. SIMD mode, you could just do multiple operations. It's faster, but remember, CPU can only do 1 or 2 per clock cycle, maybe 5 or 6. SIMD makes it, doubles it, or 10. So still, if you're running 10 gigahertz, 1 gigahertz, doing 10 operations per clock cycle, then you're doing 10 giga operations. How do you get to the 10 exa operations, right? That's like, I don't know, 10 to the 9 cycles. So let's go back to CPU. Most CPUs today actually have DSPs built in. In fact, most CPUs today have multiple execution units. Floating point SMD are one of them. So we could increase operations. Again, probably 100 operations, plus or minus, probably is a limit. Okay. So, conclusion, CPU is a poor choice to really do AI operations, or big AI operations. Simple thing, cruise control, it might be able to, because it's a specific events. Pattern recognition, voice recognition, video recognition, probably not. So next thing, okay, Nvidia is very big on this. They used to call this GPU, General Purpose Processing Graphics Processing Unit. Their benefit, GPUs, we all know, they calculate triangles really well. Angles, differences, they could zoom in, zoom out. Okay? So they have a lot of 8-bit, 16-bit multipliers. So they could do massively parallel operations, which is nice, but what's the limit? They have thousands of execution engines. Okay, 1,000, let's say 1,000 execution engine run 1 gigahertz. Actually, don't run that high, but 1 gigahertz, that's only 1 tera operations per second. Again, it's not really in the scale of exa operations. It could do it, it just does it slowly. If you want your training, some things is possible. The training could take 30 minutes, 1 hour, 2 hours. But would you want to train your, let's say when you unbox your new phone, do you want to say, hello Siri, for a whole day? Right? You don't want to. They don't. You don't do it on the your phone. It's done offline. And the big servers running, processors coming up. So GPUs, how do they use it? It's always heterogeneous. They divide up tasks between GPU and CPU, which is nice. But this is Nvidia's slide. Even Nvidia says GPU workload is about 5%. It's not very efficient. It's not very high performance. It could do very well for 5% of the time. 95% is stalled. So, we come to toward the end. This is one example. It does well. I have to, I know CNN and other companies do this. I do this. This is a wave process, Datapath, data flow processor. MIPS is now owned by same people who own wave computing. So I do that. And there are many companies working on this. Couple of things to know. It's massively parallel. I don't know how big it is, but it's pretty big. It probably takes a lot of power. But one thing to know, remember I mentioned about performance in memory terms? Any processor, you want the memory close, because you want to be able to calculate. If you don't have anything to calculate, CPU's idle. So, look how many buses it has, and places to hook up memory if you need it. Okay. It actually, if this diagram is to scale, the memory interface is just about the same size as the execution units. So basically, to do AI in any kind of real time, any kind of closer to real time, you're going to need lots of parallel resources. Today, it's going to be a lot of budget. So you're not going to do AI on a phone. You're not going to do real AI even in a PC. It's probably going to be offline or in a server farm. So you could do 3 peta operations per second. I want to go back, remind you what peta and exa was. So you could do 3 peta operations per second. And you need to go to 10 exa. Okay? So it needs to be to do, for this example, voice recognition, for wave computing, data flow processor, probably would take 3,000 seconds. And 3,000 seconds is about an hour. So it takes an hour to train Baidu's voice recognition, one voice recognition algorithm. And perhaps next time I can come and tell you how much power it takes. Probably needs almost needs its own power supply. So we're getting there, where eventually everything will become real time. There are other tricks, and they could accelerate a lot of these engines. But fundamentally, it just comes from what we know from the processor. You want the memory, high bandwidth memory, close to the processor execution engine. You want that engine to run as efficiently as possible. So, last bit. This is I'm sort of projecting. This really is starting to happen. Mobileye is autonomous driving engine, uses this algorithm, this kind of paradigm. They have a CPU, and then they have lots of execution engines or accelerators that's specific for driving. Okay? Like looking at sensors, looking at comparing sensors to make sure that the sensor is right, creating a 3D image. So ASIC is always the best option. CPU is the least benefit of power and other things, but you could do it slowly. ASIC, eventually you want to get ASIC because it gives you scalability, power, and best performance. Well, until that happens, FPGA actually is a pretty good solution. FPGA is getting bigger, and benefit of FPGA, it's programmable, right? So until I know what to implement in hardware, in ASIC, FPGA is good complement to CPU, gives you good execution engines, and then I can reprogram it to different algorithms. Maybe one time is for driving, one time is for speech, one time is for video. Probably not speech. Speech is harder. Video is easier. Security video, right? It just compares 2 images to see things different. It makes some great difference engines. So,
John, do you want to explain a little deeper about how this FPGA look like or how it's working? Right. So for some people, it's not come from semiconductor background.
So FPGA, field programmer gate array. What this is, it's a canvas for the engineer. What it does is it give you, in some ways, it gives you a lot of NAND gates. NAND gates are building blocks of electronics. So let's say I have an FPGA device with 10 million NAND gates, plus lots of memory interface. I could put those NAND gates together. It's like Lego blocks within a chip. It's software programmable, and then you could create any circuit you want. It has some limitation on how fast it could go. So some of the FPGA vendors, instead of putting just NAND gates, they put little bigger structures, like multipliers. They actually put in processors, they put in local memories, so you could actually create a processor or subsystem within a chip. And I could change it, load a different program. It's a programmable chip. So a lot of it has thousands of multipliers. Actually, this actually belongs in the previous slide. Go up there. But it's got thousands of max. You can do giga, maybe 10 giga operation multiplies or math operations per second. So this gives you enough oomph, maybe you do 4, 5, 6, 7, enough horsepower to do something. And it's a good, at MIPS we use FPGAs for prototyping. We'll put our CPUs in there, we'll test it out. Okay? Because even, well, to simulate a MIPS processor I could probably do 1 or 2 megahertz in software. The FPGA it runs 20, 30, 40 megahertz, 100 megahertz sometimes. So you could configure your algorithms, your software algorithms into hardware. When it's right, you go make 1 million chips and make ASIC, application-specific integrated circuit. But fundamentally, if we look at the paradigm, and this is what we're going to see. Microaccelerators, very small, less power, do specific functions. Look at the dedicated accelerators, that does pretty well. GPU and the DSP, which are programmable. And then CPUs are ultimately programmable. It's nice to have, not much performance on the side. It's not specialized. So, where are we looking at AI? So, we actually came out of research R&D. AI is here today. Okay? Tesla is one of the bigger ones with the autonomous driving. All other cars, I'd expect in the next 5 to 10 years will be autonomous. In fact, my teenage daughter had decided not to drive. One, mom and dad drives her everywhere. Other option is, by the time she really needs a car, 4 or 5 years, she probably won't need a driver's license. In fact, that might even be safer. So, where are we today? We're actually on this curve. AI is being more adopted. Okay? There are some robotic things. People don't have any problem interacting with intelligent machines. Intelligence behind the AI. Okay? When my kids were younger, they treated Siri like another person, had a conversation. It's actually possible. So, we're on that curve. A lot of interesting things will happen. A few things will happen. It's silicon technology. Chips are going to go faster, or possibly chips will get bigger. Well, chips have more capability because the feature sizes will get smaller. You could cram more logic onto same silicon, and it will take less power. But fundamentally, we're on this curve. We'll see what happens. Cars will be automatic. A lot of operations we do will be automatic. Sometimes it's nice, sometimes you want the control, right? So, where are we today? We're in still early stage of AI. Very much innovation left. We haven't seen anything yet. We're starting to see a glimpse of what the future might look like from the processing standpoint, from companies like Wave, companies like Nvidia. They're going massively parallel, which is fine, which is what we need. But AI is going to really require a combination of existing technology and new technologies. It's always that way. It needs to bridge us. Just remember, go back to those units. Exa, Yoda, and I forgot the one between. But we're going to learn new units. I remember being in college 30 years ago. I went to USC, by the way. Gigahertz was a big number. Okay? Some of you about my age remember the movie Back to the Future? Okay? 1.21 gigawatts, right? It was the first time I really knew what giga or giga was. Now, we're learning tera. Tera is common. Peta, exa, and these are big units. And we'll see that. We'll see that. Okay? Big numbers. So, AI takes a lot of resources. I expect fully to see in this format 4 or 5 years. So Moore's law, technology doubles in every 18 months. It'll get there. Thank you. Any questions?
Yes. I'm going to ask a quick favor. Do you mind to replace that 2 slides before this one? Sorry.
That's okay. This one?
Yes.
Yes.
Thank you.
I'll make the slides available
Oh,
to
cool.
Simon and you.
Oh, thank you. Really appreciate
Yes.
Oh, since you went to college 30 years ago, I really appreciate that data. So what kind of advice would you be giving to younger engineers, for example, like late 20s, early 30s? Should they prepare themselves to be multidisciplinary, like yourself? Or should they focus on something like hardware design or software design or whatever?
So there used to be a discipline that I used to say. I'm a firmware engineer. Okay. I haven't run into many firmware engineers in the last 5 years. So you got software engineers and you have hardware engineers. Firmware engineers guy sits in the middle, right? He's going to write the low-level code to bring up microprocessor, optimize peripherals, first bring up. So my advice would be to young engineers, do what you want. If you want to do hardware, that's your passion, do that. If you want to be software, do software. And then if you want both, then you sit in the middle and you get to both. But then your specialization is not hardware software. Your specialization is both. Which is, think about doctors, right? They have general family practice doctors that does everything. He's not going to do surgery, but he will know when you need a surgeon. So engineering is like that. You do what you're good at, what you're interested in.
Yeah.
Yeah.
You just compare the definition and like the performance across all the like CPUs and
Right.
DSPs. Can you compare the pricing? So while I was in college, they are saying that FPGA's bottleneck is like the price.
So, okay. Let me go back to a few slides before. That's a good question. Pricing is a tough thing to do. You saw I did some marketing. I don't like doing marketing. But, okay, the pricing is this. From the top, CPU is fairly expensive. DSP is fairly cheap. The reason for that is it's not technology, but it's historical. Okay? When you buy a PC, do you care whether it's Intel, AMD? Yeah? DSP is not shown to the customer. You have DSP in your notebook. You don't know whose company it is. Okay? So pricing is less. Floating point comes with the CPU, which is fine. GPU has gotten more expensive. In the last 5 years, GPU, 3D graphics, has become more expensive than its processor. Used to be it was cheap. Okay, 1998. Let's see. When I was at HP, 1998, Intel CPUs were running $500 to $1,000. GPUs $30 to $50. When I built my new PC a year ago, my CPU was $300. My GPU was $600. So it depends. Because it's popular, 3D is popular, everyone wants to 3D. 3D is expensive. Data flow processor, all right. Wave computing, their chip, $1,000, $2,000, $10,000. We'll see. Okay. So data flow processor, it seems that more specialized you are, more expensive. Unless you got lots of competition, then it becomes stripes down. Okay. FPGA is that case. It's a volume based. If I buy a Vertex FPGA, I might pay $5,000, $6,000, $7,000 each. When Cisco buys the same FPGA, when they buy 10,000, 100,000 at a time, they might only pay $500. So it depends. FPGA is something that depends on volume. Everything else, you probably, volume pricing is not much different than unit pricing. So pricing wise, things might be $100, things might be $1,000, things might be $10,000 to $100,000. Wave computing, data flow processors like wave computing and other companies, since they're in the early phases, They might be very expensive. But we know in electronics, once you have 2 or 3, 4 competition, price will go down quite quick. The first couple of guys make all the money, 90% of the money. 3, 4, 5 guys, they share the 10%. Yes?
I think that to follow on to your answer, I think Nvidia is offering an acceleration box. It's like like 1 or 2 CPUs and
Right.
multiple Nvidia GPU cards, and the pricing I think it's like $60,000 or 6 figures. I can't remember.
Yeah, because it's the early phases.
Yeah.
So it's a system developer kit that's not designed to be sold to consumers. Right? It's different. So the one I was talking about is consumer pricing, or the developer pricing. Oh sure, my graphics card mentioned in '98 that I paid $30 to $50 to put in HP machines. My engineers were using $1,000 cards, okay, because I wanted my engineers to not waste time waiting for compilation. So it's engineering pricing is different. Yes.
You mentioned that CPU, you were using about 15 to 20% of the CPU. Is that, what type of application is that you're talking about?
It's probably, okay, the application is, there's 2 applications. There's a linear application like math processing. Okay? Those, because you know what the processing is going to be, you could optimize for that. And you could get 70-80% efficiency. That's assuming you have the memory bandwidth. The application I was talking about is like PC, like tablet, a computing platform, where where the in-user interaction, or a lot of things are happening.
Generic.
Yeah. So something running an operating system like Linux or Android or Windows.
And you said something that the processor is going to be about the same size but more gauge, but I thought we're reaching the point where the gauge size is so small right now that it's not quite feasible to make it smaller.
That's what I keep thinking. So I know that in 1987, when I took my semiconductor physics class, I still have the textbook. In the first line, one of the lines it says is, someday silicon technology will be below 1 micron, okay? Which is 1,000 nanometer. So the smallest design that I've seen, I'm seeing 8 nanometer designs and smaller. Yes, I think we're getting to the point where silicon might have run out of, CMOS might have run out of space.
But we are getting close to the wavelength of light now.
That's correct.
So once we get to that point, there is no way of lithography, using some form of lithography to etch those.
That's correct.
So that would probably be the limit, right, of that technology.
That would be the limit of the silicon CMOS. Yes. There's some other research going on. So I think we'll hit that limit probably within the next 10 years. In fact, we're already getting there. The CPU frequency, Intel frequency is good gauge. It's been stuck at 4 gigahertz for the last 15 years, 20 years almost, right? 3 to 4 gigahertz. Because they'll get smaller. They could make it faster, but not much faster. So we're at the tail end of CMOS. Somebody smarter than me, smarter than me will come up with something.
But I thought actually multi-core processor speeds are lower now, right? Because of thermal requirements for all of those things.
That's correct. Thermal requirements, and then to get a signal from one end of the chip to the other end of the chip, it takes longer. So as long as it gets bigger, then it's tougher. Like Nvidia and Wave, their chip is probably very big, and it's probably limited by how they design. How they design is limited by how much light electrons could travel in a second. So